Well, good morning, students. Welcome to Monday, April 13th, 2020. Hope you had a good spring break. Hope you had some time to put aside some of the schoolwork. Also hope that you use some of the time to catch up on some schoolwork if you need it. I know I spent a lot of time on school stuff. Actually, I'm here on Friday to making video for you. And I've done a lot of grading papers. But I've also had some time out in my yard and playing with some things at home. Played some games with my wife, a couple of rounds of Thanos. If you're looking for a good board game, Thanos Rising, based on the Marvel comics. Oh, it's a good one. Anyway, let's get into it. We're starting a new chapter here. So, all right, our learning targets today. I can define the physics concept of work and perform calculations involving work. Okay, now, physics concept of work. Work can mean different things for different people. Okay, we're going to get into the physics part. So, it is a new chapter, chapter 5. The topic of this chapter is work and energy. So, what is work in a physics sense? Now, today I came into work and I've been typing on keyboard, rearranging some things. I'm now standing here talking, and for other people, their work might involve out plowing a field. Their work might involve, carrying and lifting and moving things. Some of those are their jobs. Okay? Now, in physics, work is not just your job. In physics, work is the transfer of energy through motion. Transfer of energy through motion. The most common way that is calculated is with a very simple looking formula. Work equals force times distance, change in position, change in displacement. Work equals force times distance. So if you look at that formula, work equals force times distance, and we know that force is measured in newtons and distance is measured in meters, well, that's going to give us our new unit. It's called a joule. The unit of work is a joule, given the symbol of uppercase J. And a joule is equal to a newton times a meter. And you can think back and say, well, a newton was a kilogram times a meter per second squared. So if we took a kilogram times a meter per second squared times a meter, we'd have a kilogram times meter squared per second squared. Isn't it a lot nicer to write joule instead of all that? Okay? But this is what the unit of energy would be in terms of fundamental units. Kilograms, meters, seconds. Those are all fundamental units. This is a derived unit. All right. So, simple enough. Let's work through a couple of examples. Number one, how much work is done in lifting a 170 kilogram bar a distance of 0.55 meters? So here's our new formula. Oh, I'll leave the delta D in there. Work is force times distance. So on your sheets that you're already using with formulas, we should probably add that one. Okay. So we look at our equation and we say, do we know a force and do we know a distance? And I can see right over here, I got a distance. Here's where students make mistakes. That's not a force. 170 kilograms is a mass. So now let's think about it. Okay, I got a bar. I'm going to lift this bar. How much force does it take for me to lift that bar? Well, I'm going to have to exert a force at least equal to the weight of the bar. Oh, wait a minute. The weight of the bar is m times g. I know the mass, so I could find 170 kilograms times 9.80 meters per second squared. Get out our calculator. $170 times 9.8 equals 1,666 kilogram times meter per second squared is newtons. That would be 1,700 newtons to 2 sig figs. Look, that's newtons. That's a force. If I'm lifting a bar, I have to exert a force at least equal to the weight of the bar. That's a physics concept that you got to apply and get ingrained in your head. So now, all right, to lift this, I'm exerting a force, and I'm going to keep this number while I write it in, and I'm going to round off at the end. 1,666 newtons times 0.55 meters times 0.55 equals, now I'll round off my final answer to 2 sig figs, and I'm going to have 920 joules is my answer. Please be careful that you recognize the difference between force and mass. Force is given in newtons, or in English system in pounds. Mass is given in kilograms. Okay? And I know that in common usage, those terms get kind of sloppily mixed together. But for our physics problems, there's a difference. We have to get that. Example number 2. By the way, I didn't say this earlier, but you should have paper with you, and you should be working through these problems with me. Okay? Just watching me do it doesn't create the same connections in your brain as you working them out with me. If 1,560 joules was used to lift the crate 45.0 centimeters, what was the weight of the crate? Well, we've got joules, so we know we're dealing with work. We've got a distance. Okay, so we've got work, we've got a distance. We're looking for weight. Well, that's a force, right? So work is force times distance. Force would be work over distance. Okay. The work was 1,560 joules. The distance was 45.0 centimeters. Hopefully you got some alarm bells going off in your head right here though. Because remember, a joule is a newton times a meter. I don't want to use centimeters on the bottom. I want meters. So I have to do a little unit conversion. And this is a real basic one. You should all know that there's 100 centimeters in a meter. So 45 centimeters is 0.450 meters. And now I can see that meters crosses off, leaves me with newtons. That's a unit of force. We grab our calculator. 1,560 divided by 0.45 equals, this crate had a weight of 3,467 newtons. I should go back and see. We got 3 sig figs here, 3 sig figs here. So I'm going to go 3,470 newtons is the weight of our crate. That's a force. Okay. Good news with these videos, you can back it up and look at it again. All right, number 3. A weightlifter completes a squat and then holds the 155 kilogram bar 1.55 meters off the floor for 3 seconds. How much work is done during the 3 seconds? Work equals force times distance. And we have a mass of our bar, and we saw before that the mass, we could calculate the weight to the bar, and that's the force. But you know what? I don't want to do that, because that would be extra work in a different sense. Because here's the deal. How far did the bar move? He's holding it there for 3 seconds. And during that 3 seconds, the bar isn't going anywhere. So my distance is a 0. I don't care what my force is. My distance is a 0. He does 0 work. Boom. Done. I have this problem in here for a point. In our physics definition of work, it's the transfer of energy through motion. If there's no motion, there's no work. Okay? In the classroom, when I talk about this, I would often have a student, I say, okay, I want you to go over to the wall, and I want you to try to push the wall over. And, you know, sometimes students, they don't give it much effort. And once in a while, I have a student who really goes and pushes pretty hard on the wall. And, you know, undoubtedly, they're applying a lot of force to the wall. But if they don't move the wall, they did 0 work. Meanwhile, I can have somebody else, you know, give them this marker and say, all right, do a curl. Every time you do a curl, I'm applying a force through a distance. I'm doing some work. I'm doing work here. The guy trying to push the wall down is not doing any work. The physics definition requires motion. All right, a forklift lowers a 1,250 kilogram pallet a distance of 3.20 meters from a warehouse storage rack to the floor. How much work was done? Work equals force times distance. Oh, let's see. I have a mass and I have a distance. So I guess I'm going to find my weight, which is m times g. And so my mass was 1,250 kilograms. And g is 9.80 meters per second squared. Kilograms times meter per second squared is newtons. (1,250) times 9.8 equals 12,250 newtons. Now that would have only 3 sig figs, but I'm going to round that off at the end, not right now. So if I come up here and use that as my force, 12,250 newtons times 3.20 meters. $39,200 joules. Anybody see a problem? Force is a vector quantity. Direction matters. I've been using the word distance, but really it's displacement, because the direction of the motion here does matter. And here's the thing. Which direction is the forklift applying a force? And even though the material is moving downward, can you think about it? If the forklift wasn't applying an upward force, this stuff would just be falling at acceleration of gravity, and it's not. It's being slowly lowered to the floor. So the forklift is actually lifting up, but the displacement is down. So the force and the displacement are in opposite directions of each other. So one of those has to be a negative. And I would say the displacement is downward, so the displacement has to be a negative. So our work in this case has to be a negative. The forklift did negative 39,200 joules of work on this crate. What is that negative? What does that mean for us? See, when we do work on an object, we change the object's energy. So if we increase the energy of an object, we did positive work. If we decrease the energy of an object, we did negative work. So think about that pallet in the warehouse. When it was up on the storage rack, if you lift it up there, you're increasing its energy. How does it have more energy? Think about if it fell on you. It's got a lot of energy when it's up there. When it's on the floor, it can't fall on you so far. It doesn't have as much energy. Now, our forklift problem, we took the pallet from up here and we lowered it. We actually decreased the energy of the pallet by that 39,000 joules. We didn't increase it. I got to go back. Did I write the correct label? Yes. Okay, so it was negative 39,200 joules of work. We have to think about the distances. So direction matters. Upward force, downward displacement, negative work. All right. Billy Bob is pulling his little sister Bobby Sue across their yard in a sled. He applies a force of 105 newtons to the rope. The rope makes an angle of 30 degrees with the horizontal. How much work does he do in pulling her 25 meters? I think a diagram is going to help us out here. So there's Bobby Sue in the sled. Bobby Sue in her sled. And here's our rope. So Billy Bob is pulling a rope. The rope makes an angle of 30 degrees with the horizontal. Now, his force on the rope is 105 newtons. But I want you to think about direction. Bobby Sue is not moving in the same direction as the force. So we can't just take 105 newtons. The sled doesn't move 25 meters in that direction. The sled moves 25 meters in this direction. Okay? So, hopefully you're seeing it already. What do we have to do? We have to figure out what part of the force is pulling this way. That's a component problem. We've done a bunch of component problems. So all I have to do is say, let's see, I want this horizontal component. And the horizontal component is adjacent to the angle that we know. So I want to use my cosine function. Cosine of 30 is going to equal FH over 105. Newtons. So my horizontal component is going to be 105 newtons times the cosine of 30. My horizontal component is three sig figs, 90 newtons. For what it matters, I'm going to go just jot down 90.93. Again, I kind of like to keep extra digits until my final answer. Okay, so now we can say how much work. I'm going to extend this page a little bit. Work equals force times distance. What I did is I figured out how much force was in the direction of the motion. Okay. Now your textbook is going to give you a formula where it involves the trig functions along with it. And to me, it just makes more sense to say, let's just break this up. Let's do a component problem, figure out of my force, how much is going in the direction that we're moving. And then we use that in our work calculation. So in this case, we need that horizontal component because our distance was horizontal. Our displacement was horizontal. So I'm going to take that 90.93 newtons with 3 sig figs. Oops. And we're going to multiply that by the 25.0 meters. And I get 2,270 joules. The force wasn't in the same direction of the motion. So I figured out how much of the force was in the same direction of the motion. Sometimes work is done just to overcome friction. I told you earlier that when we do work on an object, we're changing its energy. Now think about little Bobby Sue in the sled. At the end of the problem, she's moved across the yard. But if she's not, if she doesn't have a lot of motion, let's say he pulls her across the yard and now she's just sitting in a new spot in the yard, she effectively doesn't have any more energy. He applied a force through a distance and they were in the same direction. Where did that work go? Well, there was friction holding back on the sled the whole time too. And so you could say that friction is in the opposite direction of the motion. So if you take that force times the distance, it's doing a negative work. And in that particular problem, the amount of work that little Billy Bob did was equal to the amount of equal and opposite to the amount of work that the friction did. And so Bobby Sue ends up with the same energy she had to start. Sometimes work is done to overcome friction. So I said here, if you apply a force through a distance, but the object has no more energy than it began with, you can bet friction was, pun intended, working against you. So that's as far as I want to go for this video today. Hopefully that makes sense and you can play and replay and absorb. I give you some practice exercises to work on, and see you tomorrow.